Now let's look at 2024 F equals ma problem 20. This problem gives us the following system. We have four masses, 4 amps, right? Actually, they are connected through the Ross. So basically, they form, in general, a rhombus, right? But in equilibrium, it's a special rhombus, it's a square, okay? And for each pair of diagonal masses, they are connected by a spring with a spring constant K. So when the system is in the square position, the spring is relaxed then, okay? And now we try to reshape the diagram from its equilibrium square position to some general rhombus position, right? So then after we list it, so the system will oscillate and ask us to compute the oscillation period. Again, so we will use the energy approach to solve this problem. So we need to write down the kinetic energy and the potential energy. And before doing it, we need to decide which general coordinate we want to use. Because in any kind of a position, the system is a rhombus. So the shape, and we know the side length of the rhombus, right? So let me call it L. So we can use this angle to fully characterize the shape of the rhombus. And we know because the rhombus, so two diagonals are always perpendicular, right? But there's one thing. Actually, I want to make the modification. Don't just want to use this angle as a general coordinate to measure the system's dynamics, but I want to write it as 45° plus theta. Why I do it in such a way? The intuition is if we define this angle in such a way that in equilibrium, theta is equal to 0. Otherwise, if you set the whole thing as theta, then in equilibrium, theta is 45. So by setting the equilibrium value to be 0, then when you make some analysis, should be easy. Okay. All right. And the reason I want to do it is because let's look at here. So we want to make the perturbation from the square equilibrium with a small amplitude. So it's the small oscillation, right? So we know in general that so long you make the small oscillation about the equilibrium point, so typically it's about a harmonic oscillation. But if the displacement is very big, it's not always the case that it is harmonic oscillation, right? So therefore, we want theta, we define theta in such a way. So our analysis will be for small theta. Otherwise, if we define 45 plus theta as a new variable, say alpha. So we always need to remind ourselves that alpha is a number that is close to 45. But that could make the analysis to get hard, right? Because we have enough tools to analyze data that's close to 0, not close to some other numbers. So this is the key reason. All right. So by introducing this general coordinate, now we are ready to write down the systemic kinetic energy and the potential energy. Let's write down the kinetic energy. So let's look at two masses that are horizontal. So for each one, its kinetic energy is 1/2 times this mass times the square of its displacement. So d dt square. So it's L cosine of 45 plus theta. And we have two such masses, so it's multiplied by 2. Then let's look at two vertical masses. So each one has kinetic energy 1/2 m d dt L cosine of 45 minus theta square times two masses. Okay, so this is the kinetic energy. It's a big mass. By doing some algebra, we can see that it is equal to ml squared sine 45 plus theta times theta dot square plus ml square cosine 45 plus theta and theta dot square. So it's equal to ml square theta dot square. So you write it in the standard form as the 1/2 of 2ml square times the square of the derivative of the general component. This is kinetic energy. Next, let's write down the potential energy. So for the horizontal spring, its potential energy is given by 1/2 K times its extension or its displacement. So with the angle theta, its length is equal to twice of L cosine 45 plus theta. And its relaxed length is twice of L cosine of 45. Okay. And then let's write down the potential energy for the vertical spring is twice of L cosine 45 minus theta minus twice of L cosine 45. Okay. So for this one, we need to make some simplification, and it is essentially equal to KL square times cosine of theta minus sine of theta minus 1 square. So this is just the basic algebra. Okay. All right. So next, we need to make some approximation that theta is pretty close to 0. So for small theta, we know cosine of theta could be approximated as 1. Sine of theta can be approximated as theta. So it has the approximation as twice times theta squared. Okay. All right. By having this, we can compute the first order and second order conditions. The first order condition is 4KL squared theta. So we can easily see that the equilibrium is theta naught is 0. And then we compute the second order condition about the equilibrium point. So it's simply 4KL squared. All right. So now we are ready to compute the period is equal to 2 pi times the numerator should be the second order derivative of the potential energy. The denominator should be this guy. So the answer is 2 pi times oh, I made a mistake. My bad. Yeah, so the denominator should be 4KL squared. The numerator is 2mL squared. Yeah, so now it is correct. So it is m over twice of K. Let's see which choice is correct. It's B.